He is from University of Glasgow, and his title is Structure and Behavior of Proteins with Molecular Activity. Please take it.
Good morning, everybody. As I've said several times before, I'm enjoying this visit immensely. Wonderful scientific program, beautiful city, fantastic. So I'd like to thank Russell and Raphael again for coming up and inviting me. Now, today's talk is rather different from the one I gave here nearly 2 weeks ago. That one was on fundamental symmetry aspects of chirality and the implications for absolute enantiomer selection, possible fields and forces that could generate small enantiomeric excesses of all these wonderful mechanisms we're hearing about could boost the high homochirality. And there I think that the key thing of that talk was the introduction of a new definition of chirality, which takes account of sources of chirality when motion is important, like when you've got translating spinning systems. I introduced the idea of true and false chirality. False chirality means something that looks like chirality but isn't really. Anyway, that is now apparently on the web if anyone wants to catch up on that. But today this is something rather different. I'm going to tell you about some new insights into the protein structure and behavior, especially with regard to the tremendous importance of water and solvation, and possibly significance of homochirality as well, that has come from studies I've done over many years using a fancy novel form of chiroptical spectroscopy called Raman optical activity. So, first of all, basic stuff. This is a few of the first slides I showed in my first talk. So chirality then, it's tremendously important. More and more interest is developing in it. It pervades much of modern science, from the physics of elementary particles through organic stereochemistry to structure and behavior of the molecules of life, and much else besides: nonlinear optics, nanotechnology, electrical engineering, pharmaceuticals, etc., etc. And for our interest here is that life is based on homochiral chemistry, so hence the importance of chirality, the origin of life, and astrobiology. Then we have Lord Kelvin's original definition of chirality, which is still the definition we use in stereochemistry today. But of course it all started 50 years earlier with Louis Pasteur's wonderful discovery. And proteins, now looking at the molecules of life. Proteins, of course, consist of polypeptide chains made from combinations of 20 different amino acids, all exclusively the L enantiomer. Nucleic acids are built from chains of deoxyribonucleosides or ribonucleosides connected by phosphodiester links, 4 different bases, and only D-ribose sugars occur. And I think most of us agree that homochirality appears to be an inevitable characteristic of the chemistry of any molecule-based life. Something a bit more controversial, the question of the ingredients, carbon, water and life. I am of the opinion, which is shared by lots of people but not everyone, that it has to be based on carbon chemistry, organic chemistry. No other element than carbon forms such a huge variety of compounds, many of them chiral. No other element has such a propensity for concatenation, especially important for backbones of polymers. Now, liquid water, it's the absolutely essential medium for life on Earth, but it's not just a medium. It's more than that. It acts as a lubricant of key biochemical and molecular processes. And this is something I'll emphasize later on in the talk. No other solvent can be envisaged as having the necessary physico-chemical properties. They're unique to liquid water. So my current prejudice, if you like, is that life on other worlds, if it exists, will probably be based on a homochiral organic chemistry in an aqueous environment, even if it originated independently from life on Earth.
You ignore sulfur and phosphorus.
Yes.
I think sulfur and phosphorus are also very important.
Oh yeah, as subsidiaries to carbon.
But without them, you would not have.
Oh, absolutely. Oh, there's lots of other. Of course, we need many other elements, but it has
Not many. I think phosphorus and sulfur, in
Okay.
addition to carbon, are
Okay.
also essential.
Okay, but for example, people talk about silicon instead of carbon. You see, I wouldn't go along with that. So, water and proteins. The importance of water in protein science has long been appreciated, especially its role as a lubricant of structural transitions and its ability to induce conformational flexibility, which is tremendously important in protein folding and function. Also, hydration is especially important in stabilizing sequences in proteins that are unfolded in their native biologically active states. There's more and more proteins being discovered that are completely unfolded in their functional states. It used to be the paradigm of protein science, the central paradigm that, structure and the fold determines function. That's no longer absolutely the case. There's many, many proteins being found now that are completely unfolded in their native functional state. And they undergo disorder to order transitions in their function. And does chirality play any role in such disorder to order transitions? If so, it could be a significant factor in discussions of the origin of prebiotic functional polymers. Anyway, the molecular details of hydration and how it influences structure, folding and function, they're difficult to study in aqueous solution, but this fancy chirotical technique called Raman optical activity that I've battled with for many, many years is turning out to be especially valuable for studying this problem. So, Raman optical activity, what is it? ROA for short. It's a form of polarized Raman spectroscopy that probes molecular chirality. Like conventional optical rotation and circular dichroism, it relies on the fact that chiral molecules respond slightly differently to right and left circularly polarized light. But whereas circular dichroism measures optical activity in electronic transitions, ROA measures optical activity in vibrational transitions. That means it can provide much more structural stereochemical information because it reports on all 3n-6 fundamental vibrational transitions rather than just the odd chromophore you might have. So just as conventional vibrational spectroscopy has many more structure-sensitive bands than a conventional UV visible absorption spectrum, so the vibrational optical activity spectrum has much more structural information than an electronic CD spectrum. Anyway, we found ROA can be applied to a vast range of chiral molecular structures, from small organics through synthetic polymers through to large biomolecules and even intact viruses. We can get some very good results. So Raman spectroscopy itself, I'd better very briefly remind you, this is people often even today, Raman is very important in all sorts of areas, but it doesn't seem to get the emphasis, say, in infrared absorption in undergraduate courses. So you have molecular sample, incident laser beam frequency omega, light scattered in all directions. This could be, for example, a solution. We work in aqueous solutions. Light scattered in all directions. You sample the light scattered into a particular direction, pass it through into a spectrograph. You'll find most of the scattered light has the same frequency omega as the incident light, that's Rayleigh scatter, but tiny frequencies are scattered with, tiny components are scattered with frequencies displaced from the incident laser frequency by one of the vibrational frequencies of the molecule. And that's called Stokes-Raman scattering. So by analysing this spectrum of the visible scattered light with the visible spectrograph, you can get a vibrational spectrum. So Raman provides vibrational spectra via inelastic scattering of visible light. As the photon bounces off the molecule it steals a vibrational quantum of energy from the photon. So this is the sort of visible spectrum you will get. At zero frequency shift, that would correspond to the frequency of the laser beam, say 532 nanometers is a common laser we use these days, a nice green colour rather like this laser pointer. You get a very, very intense Rayleigh band, and as you come away to lower vibrational frequencies, you get all these little lumps and bumps which correspond to all the various vibrational Raman bands. Now there's two equivalent ROA experiments. The original experiment we used to do, it's called incident circular polarization, ICP-ROA. So here's your chiral molecule. You measure the Raman spectrum in right circularly polarized incident light, measure it in left, and take the difference. If the sample's chiral, there will be a difference, and so that's the ICP-ROA observable. You could do the experiment the other way round. You can use unpolarized incident light and measure tiny right or left circular components in the Raman and various Raman bands in the scattered light, and we call that scattered circular polarization ROA. This SCP-ROA has got significant advantages over ICP, and it's the basis of a new generation of commercial instruments. The first observation, which I made working in David Buckingham's laboratory in Cambridge in the early 1970s, we used this method. This is much easier to implement. So here's what typical ROA spectrum of a small chiral molecule will look like before we get into proteins. So here we are, 1-phenyl ethanol, so that's the R plus enantiomer. So at the top here, that's the conventional Raman spectrum running from about 100 to 1600 wave numbers. Some nice, strong, sharp vibrational Raman bands. Here's the ROA spectrum of the R plus enantiomer. So that spectrum there is that one measured in right circular minus that one measured in left. So it's a signed quantity, positive or negative about a zero line, just like a CD spectrum, except there's many more structure-sensitive bands. You're just drowning in stereochemical information here, in fact. Put in the mirror image enantiomer and it all turns upside down. It's a very tiny effect. The biggest bands here, the ratio of the difference to the sum is about 1 part in 1,000, but we're sensitive to about a part in 100,000. It's a very small effect, so it really pushes modern electro-optic technology to the limit. This experiment has a voracious appetite for the latest developments in electro-optical technology. Anyway, I don't have time to go into the theory. If anyone's interested, you'll find it all in this new edition of my book. Now, for small chiral molecules, the best way to get information out of an ROA spectrum is via ab initio quantum chemical simulations of the spectra. So you would compute the spectrum for a given absolute configuration and a given conformation and see how it compares with the observed spectrum. And in fact, over 10 years ago now, we used ROA with an ab initio computation to determine the absolute configuration of this archetypal chiral molecule CHFClBr. It had been known for over 100 years, but for very good reasons. Its absolute configuration wasn't known. Conventional techniques couldn't deal with it. So this is what we found. That's the S plus and R minus. But last year, in a real tour de force, Werner Hug in Switzerland really pushed everything to the limit, including organic synthesis, to make this chiral neopentane. It's chiral due to just isotopic substitution, CH3, CH2D, CD2H, CD3, no measurable optical rotation or circular dichroism, inaccessible to any technique. So he believed for absolute configuration determination, but he got the correct, he got the absolute configuration from, simulating the spectrum, comparing it with the measured spectrum. which was just about detectable at about 1 part in 10 to the 5 on his latest fancy homemade instrument. Anyway, anyone can do ab initio ROA simulations these days using, it's available in the Dalton and Gansky software packages. Right, on to biomolecules. ROA is much more incisive than conventional vibrational spectroscopy for studying biomolecules. And the reason is, it's the sensitivity to chirality that does it, and it's similar for circular dichroism, in fact. Vibrations which sample the skeletal chirality most directly make the biggest contributions to the ROA intensity. So here's the polypeptide backbone of a protein, here's amino acid side chains. The conventional Raman spectrum of a protein is dominated by bands from vibrations of the amino acid side chains. There are peptide backbone bands there, but they tend to get swamped. Whereas protein ROA spectra, they're dominated by bands from the peptide backbone, because it's the most rigid, twisted chiral bit of the structure. The side chains, you have more conformational flexibility, which tends to suppress the ROA. You still do get side chain bands, but the best bands come from the backbone. So, you know, ROA gets right into the chiral guts of biopolymers. I like to say that ROA reaches those parts other spectroscopies fail to reach. Those of you who remember the old Heineken advert will appreciate it when I call it the Heineken of spectroscopies. So here's the ROA spectrum of typical protein in lysozyme. It's got a nice, relatively simple fold, mostly alpha helical domain, a little bit of beta sheet, and all these loops and turns. That's the spaghetti that holds it into its fine three-dimensional fold. So here's the conventional Raman spectrum. We can get down to about 200 wave numbers in proteins now with this new commercial instrument. So here's the ROA spectrum. All these little lumps and bumps are real and reproducible. It's just overwhelmed with structural information here. Just point out a few features. This stuff here at about 1650 wave numbers or so, that negative positive couplet, that's coming from the amide 1 vibrations. That's the backbone CO stretch, and that negative positive couplet, it's associated with both helix and sheet. That positive band there is about 1300, and that one at 1340, they're both alpha helix bands. But what's so important here is we have lots of evidence to support the assignment of the 1300 to unhydrated alpha helix and the 1340 to hydrated alpha helix, and that's turned out to be extremely valuable. So the vibrations here, that's what's called the extended amide 3 region. That comes from coupled CH and, comes from C alpha H and NH deformations of the peptide backbone. And it's very sensitive to the phi psi, the Ramachandran phi psi angles, which determine the different structure. Alpha helix has certain ranges of phi psi, beta sheet ranges of phi psi, and you get very characteristic patterns for different protein folds. Here's just 3 examples. This is an all-alpha fold, serum albumin, nice characteristic patterns there. This is an all-beta fold, intact human immunoglobulin. You have these 12 beta sheet domains. Another pattern, quite distinct from the alpha domain, and here's a natively unfolded protein, beta casein. We started to realise early on that we could actually just read off the folds from the patterns and could recognise them with experience. So the importance of ROA here is as well as detecting secondary structure like you get from conventional CD and ion, for instance, you get an idea of the tertiary structure, the three-dimensional fold as well. And anyway, more recently we've been putting this this identification on a more scientific basis using pattern recognition methods, multivariate analysis. In particular, a method called nonlinear mapping we've been using recently, which is very good. Anyway, I'm not going to go into that at all, but just show you, this is the sort of result you get from nonlinear mapping. This is a projection of data into two dimensions. So this pertains to our data set, which has something like 80 or 90 different polypeptide protein virus ROA spectra. Each of these colored dots corresponds to a complete spectrum. And the idea is that the closer the dots are to each other, the more similar are the patterns, and hence, hopefully, well, it turns out to be the case, more similar are the structures, including the fold. And you can see they cluster very nicely according to these basic structural types. So this red cluster here, that's all alpha proteins. The only secondary structure element is alpha helix. No beta sheet, all the rest is spaghetti, loops and turns. Likewise, the dark blues, that's all beta, that's the only secondary structure element. And the light blues, that's mainly beta with a little bit of alpha, and so on. So left to right we go sheet to helix, but top to bottom we go order to disorder. Coming down here, these are more and more disordered structures. So these grey ones, they're completely disordered polypeptides, for example. And these greens, those are mostly natively unfolded proteins, and this is what's particularly important for this talk. Now here are average spectra, so averaging, say, over the spectra in that all alpha region, you get that spectrum there, averaging over the all beta, you get that spectrum there. So you can see, you could use that as a model spectrum of an all alpha protein and all beta. You see, they're quite distinct and easily recognizable. Now that one there, that is the average of the all disordered structures. And that's characteristic of something we call, well, something known as polyproline 2 helix, which is attracting a lot of attention these days as an important structural element in so-called disordered, unfolded polypeptide sequences. Now here, down here, this is the greens. This is mainly disordered, and you can see that that's dominated by this all disordered spectrum here, with a few other little bits and pieces showing it's not pure polyproline 2 helix. And that spectrum there, that's characteristic of many natively unfolded proteins. The synucleins, for example, brain proteins, synucleins, alpha synuclein, that gives you Parkinson's disease when it misbehaves and aggregates, for instance, and tau gives you Alzheimer's the proteins, caseins and whatnot. They all have spectra looking quite similar to that. So, let's have a look now at this polyproline 2 helix structure that seems to be dominant in disordered polypeptide sequences. A long time ago, Tiffany and Krim, 68, from CD data, they suggested that disordered polypeptides are not random coil. People have always thought, and this is in classic polymer physics, the default disordered structure, it's a dynamic random coil. All torsion angles are being sampled over a certain time span. Well, they suggested that this isn't the case in disordered polylysine polyglutamic. They suggested that this polyproline 2 helix is an important conformational element. It's not a random coil. It's an extended left-handed helix. It's the NH and CO groups are too far apart to support intramolecular hydrogen bonds like in the alpha helix. Instead, it's stabilized by water hydrogen bonds to the side chains and also to the CONH backbone as well, and that stabilizes the polyproline 2 helix. But at the same time, it means it's rather flexible. So anyway, this is the famous Ramachandran surface. This is those torsion angles phi and psi. And this gives you the potential energy as a function of the various values of the phi psi angles, which can range from minus 180 to plus 180. You've missed the best bit. Shall I start here? So anyway, this is the alpha helix region on the Ramachandran surface. So you have a well here that corresponds to the alpha helix by psi angles. Polyproline 2 lives up here next to the beta strand region, beta strand, beta sheet region. So PP2 lives up there, alpha helix down here. So it's left-handed, and those are the phi psi angles that determine the classic PP2 symmetry. So there it is. Now, just to give me as well as you confidence that we are correctly identifying this signature of polyproline 2 helix. It's still quite controversial. More and more people are accepting that PP2 is a significant element of structural element in unfolded, disordered polypeptide sequences. There's still some sort of hardcore of people who are saying, "Oh, this is nonsense. It's still the dynamic random coil. This is approximation and whatnot." So anyway, so there's that all disordered. That's that average all disordered spectrum I showed you. This strong positive band at about 1318, 1320 wave numbers. That's the most characteristic peak. Now this is a 7 residue model alanine peptide. Designed to support the PP2 conformation in aqueous solution, and that's been confirmed by NMR. A combination of NMR and CD has confirmed that is dominated by PP2. That was from Neville Kallenbach's group in New York. Neville is a close friend of Mark Green, who entertained us 2 weeks ago. And anyway, so that's the ROA spectrum of this 7 of this model peptide. You can see it's very similar to that all disordered one there. But then we've recently done an ab initio simulation. We're starting to extend ab initio simulations to extended uniform polymer conformation. So this was a 10 residue alanine peptide held in the model PP2 conformation. And this is a simulation of the ROA spectrum, and it's pretty good for this sort of thing. That's almost as those correlations are almost as good as you can hope for. Just changing the phi psi angles by 5 or 10 degrees changes this spectrum utterly. So we're pretty confident that we really are very sensitive to the PP2 conformation through this characteristic ROA spectrum. Now, on to protein misfolding and disease. And you see there is some relevance here to our interest in origin of life. This is a big industry these days. Alzheimer's, Parkinson's, the prion encephalopathies, amyloidosis, etc. They're protein misfolding diseases involving formation and deposition of amyloid fibrils. So here's your folded protein. You can have partially folded, denatured intermediates, and you can have completely unfolded proteins, either denatured ones or these increasingly important natively unfolded proteins. Anyway, these partially folded and unfolded proteins have a propensity to aggregate, and in special situations, normally you just get amorphous aggregates. But in special circumstances, you get this regular, extended so-called cross-beta sheet formation when they sort of, the chains stack together in this regular arrangement. And these are very, very long, form very, very long strands, and these associate into famous amyloid fibrils, which deposit in the brain and other parts of the body and cause all sorts of nasty diseases. Anyway, ROA has provided insight into structural elements, especially polyproline 2 helix, within unfolded and partially folded proteins that may encourage the so-called fibrillogenesis. Now, this is an example of the sort of evidence we have that put us onto this. Now, this is human lysozyme, similar fold to the hen lysozyme I showed you before. Very similar ROA spectrum. That's an example of, how you can just read off a fold from the appearance of the spectrum. If you didn't know the fold of human lysozyme, but you got the ROA spectrum and knew the fold of hen lysozyme, you could say straight away that that's a very similar lysozyme fold. The pattern is so similar. Anyway, human lysozyme has an interesting characteristic. If you heat it up at pH 5.4, that's the native. If you heat it up, pH 2, heat it up to 57 degrees, over about 24 hours it forms genuine amyloid fibrils rather than amorphous aggregates. This is associated with what's called amyloidosis, a very nasty disease in which you can get kilogram quantities of amyloid depositing in various organs, lungs, liver, heart, and that's due to a mutant lysozyme. It runs in families, just replacing one or two amino acids in the sequence destabilizes it just a little bit, so it still functions, but in sort of 20s or 30s, it can start to aggregate and give you amyloidosis. Anyway, so it forms genuine amyloid fibrils under these conditions, and that's the ROA spectrum of this prefibrillar destabilized material. This is still in solution before it's aggregated. And now here you see this is our famous hydrated alpha helix band at about 1340. It's completely gone in the prefibrillar protein, but what we've got instead is a lot of intensity here and characteristic of pp2 helix. So this suggested to us that hydrated alpha helix was melting in the first instance the polyproline 2 helix, and maybe polyproline 2 helix was what we called it in our first paper on this, the killer conformation, perhaps. This is what's doing the damage. So here's the polyproline 2 helix again. It lives here in the Chandran's surface. So the idea is, you see, you have these long strands of pp2, very close to the beta strand conformation, and it's hydrated, it's stabilized by hydrogen bonded to water here, water molecules, hydrogen bonded to NH and CO. You can see elimination of water molecules between the strands to form beta sheet is highly favourable entropically. So you take 3 waters out here and you'll form an NHCO cross-strand hydrogen bond, so you'll form beta sheet. And it'll be nice uniform beta sheet rather than amorphous aggregates, you see. So this is the idea. Maybe PP2 is the killer conformation. Well, it turns out that there is some an element of truth in this, but you have to qualify it because you have all these natively unfolded proteins and unfolded sequences in proteins which don't aggregate, they're protected from association. The reason is that the balance of the physicochemical properties of the amino acids have been tuned by evolution over millions or billions of years to resist aggregation. It's, for example, what you want is you want low net hydrophobicity. That will inhibit this sort of process, and you want high net charge in the amino acids. That tends to push the chains apart. And so that's what's going on. In natively unfolded proteins, that the sequences have been tuned by evolution to resist association. But when you denature a protein, a folded protein, and reveal polypeptide sequences, unfold them, they haven't been tuned to resist association, and so boom, you can get aggregation. And so that seems to be quite a valid theme. So here we are then. Let's look at prebiotic polypeptides and aggregation. So the lowest energy default structure of random heteropolypeptides is actually beta sheet and associated aggregates. That's the lowest energy conformation. That's where, proteins, in living systems, they're on the knife edge trying to resist falling down into the lowest energy state, which is the beta sheet. So life is a struggle against beta sheet formation. So that this could be amorphous aggregates, but also ordered structures like amyloid. So evolution has selected constituent amino acids of unfolded functional heteropolypeptide sequences, so as to inhibit association and hence aggregation. So I would suggest then that random heteropolypeptides, all homochiral, but hetero in regard to the mixture of the 20 amino acids, random, they're unlikely to have been early prebiotic polymers. They would simply aggregate with billions of years or millions of years of evolution to tune them so they don't aggregate. Now that still leaves the possibility of hydrophilic homopolypeptides, homochiral, like say polyl-glutamic acid, polyl-lysine could be early prebiotic polypeptides, because they don't associate, they do maintain a PP2 conformation. Also, maybe polyglycine containing a few homochiral amino acids.
I didn't understand the third point you say. Random heteropolypeptides?
Yes.
What do you mean? These are the sequence?
Yeah, the sequence is random with regard to
DL and DL?
all L.
All L?
Yeah, see, I'm saying homochiral, they're all L.
Yeah.
But you can have alanine, serine, tryptophan, phenylalanine, just random, random sequence of the 20 amino acids. They will aggregate. There's more possible combinations of sequence than I think there are atoms in
There's
the
a
universe or
statistical
something.
study of Luigi Luisi. He
Yes.
calls it never-born protein.
Yes.
He did exactly this kind of study where he synthesized random heteropolypeptides. And as far as I remember, 10% do fold into native conformation.
Really? 10%
10%. Yeah, so
my impression was it was tiny fraction will have a
that's what
fold.
many others also expected, but the result is, according to
Okay.
him, 10%.
Okay, that's interesting.
Yeah, so it depends very much whether they are hydrophilic or hydrophobic.
Yeah.
The question, the moment you're
Yes.
inserting hydrophobic part, and they have a tendency to assemble into beta sheet.
That's right. If they're mostly hydrophilic,
Yeah.
I mean, was his truly
That's it.
random, or had he
Yeah,
pre-selected?
this is what he claims.
Yes, you see, maybe he pre-selected.
Well biased, unbiased, so every amino acid.
But when he said fold, did they really have a well-defined fold, or was he just taking aggregates as common?
No, let's say what they can separate the aggregate from the cleanly folded, unimolecularly folded.
Okay, which should
protein.
still be soluble.
And yes, it's soluble, and this is what they did, mainly based on CD studies. So
NMR also.
NMR also, yes.
Peter Strajewski.
That's
Just
actually,
a paper that appeared in Chemical Biochem.
Yeah, I'd like to have the reference to that.
I got it yesterday.
Okay. Yeah. Anyway, I think that there's still an element of. I think this is still a significant concept, though, that random heteropolypeptides do have a high propensity to aggregate. Well, yes, viruses. This. I've got a couple of slides here showing you some results on viruses which reinforce our assignment of this positive 1340 ROA band to hydrated alpha helix. Most viruses can't be studied using X-ray diffraction or NMR. There's a few dozen X-ray structures, crystal or fibre, and they're immensely valuable. They're absolutely fantastic to have them. But most of the 7,000 or 8,000 different viruses currently recognised are completely inaccessible to X-ray diffraction or NMR. They just won't crystallise. Too big for NMR. Anyway, it turns out ROA can give information about both protein and nucleic acid structure of most viruses, including filamentous, cylindrical, and icosahedral types. And these results have reinforced studies of protein hydration. Now here's tobacco mosaic virus, for instance. Helix of RNA down the middle, and each of these yellow blobs is an identical copy of this helix bundle coat protein. And here's the ROA spectrum of the solution of tobacco mosaic virus, and that pattern we see there is characteristic of the sort of pattern we see from isolated helix bundle proteins. So you can recognise the folds of the coat proteins from that ROA spectrum. Now, filamentous bacterial viruses be very significant in this context of hydration. These have a loop of single-stranded DNA in the middle, and there's several thousand copies of an identical coat protein around the outside. Each of those coat proteins has the fold of an extended alpha helix, and they overlap each other like fish scales around the surface. They are overlapping like fish scales. So what you've got is half of there's about 50 amino acid residues in these helical coat proteins. About half of them are exposed on the surface, and then you have a little kink, and the other half are buried. The buried ones are mostly hydrophobic residues, those are mostly hydrophilic. And this is the sort of spectra you see of filamentous bacteriophages. That's highly characteristic of alpha helical polypeptides like polylysine. It's very similar. So, you can immediately say that the fold of proteins is an extended helix. But we have this very strong positive 1340 band, which we have good evidence comes from the outer half, the exposed half, hydrophilic residues, studies with hydrogen deuterium exchange, that sort of thing. You see this band disappear and this one doesn't, things like that. So that's supporting evidence. And here, just a little bit more evidence. Potato virus X. This is it's a very common virus. It destroys huge quantities of potato crops worldwide. There's no high-resolution X-ray fibre diffraction data available on it. It just gives very poor quality data. This is the best picture obtained so far at low resolution. So it's similar to tobacco mosaic virus, except there's much deeper grooves around the outside, which implies much more hydration of the alpha helical coat proteins. There's its ROA spectrum there. At the bottom, that's the ROA spectrum of tobacco mosaic virus, and you can see the hydrated alpha helix band is about twice as strong in potato virus X as in TMV. So that's just a little example of this. Now, on to the question of helix solvation or otherwise. There was a remarkable experiment done a couple of years ago, published in JACS. These people, they took a model 15 residue alanine-based alpha helix and heated it up in the gas phase, hoping to watch the helix coil transition unfold in front of their eyes, so to speak. Anyway, they just kept heating it and cranking up the heat, and nothing happened until they reached about 725 K, and it just fell to pieces. They didn't see a helix coil transition, and that's because it's unhydrated. You see, the hydration hydration destabilizes alpha helix and promotes the helix coil transition. Now, X-ray crystal structures of proteins reveals several different types of hydration of helices. Now this is your canonical alpha helix. It's unhydrated, and here's the key CO to NH internal hydrogen bond that stabilizes the helix. This is the most common sort of hydration observed. Water, hydrogen bonds to the CO group, and so it slightly weakens this hydrogen bond and just opens the helix very slightly and destabilizes it a little bit. Then also what's observed are three-centered hydrogen bonds with water, so this is both the CO and the NH. Also water can actually insert in between the CO and NH, so that's the sort of repertoire of hydrogen bonded water of helix elements, hydrogen bonded to water. This sort of study was emphasized by these people, Sandra Bingham and Sekarudu, in a famous paper, 1989, and they went on to suggest that these sorts of hydrated structures they were seeing actually provides a sort of a mechanism for how hydration promotes the helix-coil transition. So here's the alpha helix region of the Ramachandran surface. There's the beta PP2, and you've got this big potential barrier separating them. But some of these hydrated structures, especially water inserted, they correspond to turn structures, which actually live in this bridge region of the surface. And what they will do then is lower the potential energy of that transition, and by lowering the barrier, they will promote the alpha to beta PP2 coil transition. So we have a picture of what could be going on. So, PP2 helix and a careful disorderliness. So hydration, as I said a little while ago, it stabilizes this polyproline 2 helix, this extended left-handed helix, in a plastic adaptable manner. The potential well in the Ramachandran surface that PP2 lives in, it's very wide and shallow. So PP2 can slosh around. There's quite a lot of conformational flexibility there, but it's still within the PP2, boundaries, if you like. So it may facilitate protein folding function. You see, instead of starting from a random coil, a dynamic random coil, you've got this pre-organized, unfolded state, which lowers the entropy and reduces the conformational space to be searched when the protein folds or the sequence binds or something. We've also seen hydration destabilizes alpha helix. An ROA has shown hydrated alpha helix melts in the first instance of polyproline 2 helix. Anyway, this facile interconversion between hydrated alpha helix and PP2 structure could be important in many order to disorder and disorder to order processes. And these processes could be driven by fluctuations of water structure on a picosecond time scale. So maybe PP2 structure, it could be an important structural element to think about in prebiotic polypeptides. But with this, the sequence perhaps dominated by hydrophilic amino acids like polyglutamic, for instance, otherwise you have this problem of aggregation. So, people are always thinking of alpha helices as early secondary structures. I think maybe PP2 could be more productive, actually, to think about that as a structural element in prebiotic polypeptides. So anyway, this brings to mind one of my favourite sayings. There are some enterprises in which a careful disorderliness is the true method. That comes from Moby Dick. So, when you're chasing whales around the world, you're out for 2 or 3 years, you mustn't be too fixed in your program. If you see spouts on the horizon, to the left or something, you must be prepared to change direction and go chasing them. Well, so that's how I think of this.
Why careful disorderliness?
Oh, because it's not. I mean, a complete disorder. A random coil would be complete disorder. This is careful disorder. It's it's not complete disorder. It's disorder within certain parameters. You see, so I think that's a good concept actually for protein structure and function. It's a careful disorderliness. It can't be completely random, or you just get a mess. Yes. Well, finally, the last couple of slides. A bit of speculation here. Homochirality and disorder to order transition. So this is a little bit of statistical physics, critical phenomena. This is, I'm a complete amateur in this area. This is just sort of almost thinking aloud. It's the sort of thing, if you mention it to a physicist, he or she will say, oh, that's obvious, we've known about that for years. If you're lucky, if you're unlucky, they'll say, oh, that's just complete rubbish. So, keeping my fingers crossed. So, does the intrinsic homochirality of building blocks of biopolymers, amino acids and proteins and sugars, nucleic acids, sugars in nucleic acids, together with the chirality of the secondary and tertiary structures of the ordered state, play a fundamental role in disorder to order transitions in polymeric systems? I mean, we've seen important examples of disorder to order transitions. Order to disorder, it's melting to PP2, but it goes the other way around. PP2, what you find with these natively unfolded proteins and long disordered sequences in proteins where there's like a folded domain and an unfolded domain, those disordered sequences, when they bind to some other protein, and when they bind, very often they go over into alpha helix. So it goes the other way around. Now, might this come about via continuous second order, higher order phase transitions? The nomenclature is a bit vague. I'll call them continuous phase transitions. In a continuous phase transition, although the initial interactions are short range, the effective interactions become long range in the critical region of continuous phase transition, thereby generating long range order. So does homochirality predispose biopolymeric systems to support continuous phase transitions and hence critical phenomena? So this could generate large dynamical structures which could play a central role in directing protein folding and unfolding pathways, for example. And well, my foothold in this comes through symmetry. That's what I like to think about, symmetry, and it's the symmetry of the chiral order parameter suggests that this may be the case. So for the transition of a polymer sequence from a completely disordered conformation, let's say the hypothetical random column, although we know probably doesn't exist in polypeptides at least. So transition from a completely disordered conformation to a homochiral helical conformation, we can define a chiral order parameter with the value 0 for the completely disordered achiral structure and plus or minus phi max for completely ordered. So plus and minus will correspond to right and left-handed helices. Now, to bring the symmetry aspects in, one goes to the simple Landau theory of phase transitions, whereby the Gibbs free energy is expanded in powers of the order parameter in the neighbourhood of a transition point. So there's the Gibbs free energy, G naught, A1 phi, phi squared, phi q, phi. So this is the starting point in the Landau theory for whatever the order parameter happens to be. Now, in general, that term linear in phi is generally 0, so we can forget about that. So we've got terms in squared 3, 4 of the order parameter, and the vanishing or otherwise of these terms can be deduced from symmetry considerations. Now, a first order phase transition occurs when, at least at the simple level, it occurs when there's a term in the third power of the order parameter. That can drive a first order phase transition. But Now looking at the symmetry aspects, this gives free energy. It's a time-even scalar. That's a number that doesn't change sign under time reversal or parity, space inversion, or reflection. So that means all the terms on the right-hand side with this symmetry characteristic are non-zero. Now in the case of ferromagnetism, the order parameter is the magnetization vector. That's a time-odd axial vector. So that changes sign under time reversal. And so it means that you lose this cubic term in the expansion. And so that's one of the reasons why the ferromagnetic phase transition at the critical point is a second order phase transition. It's not first order, it's second order, and it's associated with critical phenomena. We lose that term there. Well, analogously here, instead of time reversal eliminating odd powers of the order parameter, for the chiral order parameter, it's parity that eliminates odd powers, because the chiral order parameter will change sign under parity, space inversion, reflection. So that means for a chiral time-even pseudoscalar order parameter, we have that expansion. So there's no term in the cube. So at that level, there's no first order phase transition. So you may have higher order phase transition, and hence critical phenomena. And the simple development of the Landau theory for, say, ferromagnetism, for instance, gives you this expression for the two possible values for the order parameter, and they correspond to these wells. In the ferromagnetic case, it would be all the spins pointing one way or the other. Here we've got the right or left-handed helices. So, does the ability of a system to support truly chiral observables and hence a true chirality order parameter lead to the possibility of a continuous disorder-to-order phase transition with a critical exponent of half? And as I said, I just pinched it from the simple theory of the ferromagnetic phase transition by analogy. Now, finally, one can just extend this a little bit to include the influence of intrinsic monomer chiralities. That's a message. The gods have had enough. So far, what I've said would apply to, say, polyglycine or a synthetic polyisocyanate with achiral monomers. Sort of thing that Mark Green was telling us about. Now, the influence of homochiral monomers can be incorporated into what's called a mean field Ising type model, and it's directly analogous to incorporating a weak magnetic field in the case of the ferromagnetic phase transition. So, homochirality in the monomers, or PVD enthusiasts might jump up here and say, what about that? Will alter the characteristics of the transition, and it'll bias it towards a particular absolute helical sense of the biopolymer. So now, instead of two equal minima, you get a bias. It's a bias towards one rather than the other. Here, I applied it explicitly to a polypeptide chain and took the chiral order parameter to be a function of this virtual residue torsion angle. It's a combination of the Ramachandran and phi psi angles, and it can take values plus or minus 45 degrees, so that would correspond to the maximum possible sort of chirality, if you like, in the two opposite senses, and the parameter itself has values plus 1 and minus 1 for those two things. Anyway, with just again pinching the treatment of the ferromagnetic phase transition, the mean field Ising model, the ferromagnetic phase transition in the presence of a weak external magnetic field, you find the average value of the order parameter goes as t to the half for achiral residues, and it goes as h, where h is this energy difference, to the third for chiral residues. T is a reduced temperature variable, so that corresponds to so-called critical exponents of a half and a third, which is what we have in the ferromagnetic case. So this is just very speculative, and Patrick may well want to say something or not. Now, in fact, Mark Green, when he was here, he told us that there's a theoretician called BarronC, I think it was, that developed a statistical mechanics treatment of the transition observed in his synthetic polymers to the homochiral case. And I looked at those papers, and indeed that he was modelling it on a continuous phase transition, and he called it the ferrochiral phase transition, by analogy to the ferroelectric phase transition, which is actually very similar, the symmetry of the order parameter. The ferroelectric phase transition, it's odd parity, but it's a polar vector rather than a pseudoscalar. So there may be something to this, so that's just a thought. So finally then, ROA has provided new insight into protein structure and behavior, especially with regard to hydration and to PP2 structure and its facile interconversion with hydrated alpha helix, which is very important in certain disorder-to-order transitions. Random heteropolypeptide sequences have a propensity to form aggregates based on the default beta sheet secondary structure, which implies, well, you qualified what I was saying. It's not quite as absolute a state, but it implies random heteropolypeptide sequences, still homochiral, but random in the constituent amino acids, were not early prebiotic functional polymers. And homochirality in the building blocks of biopolymers may play a fundamental role in directing disorder-to-order transitions via critical phenomena.
Director, and any comment or questions?
I don't. This statement, the Landau gives energy in the expansion. He said that the order parameter, if phi is 0, then global minimum is assumed, and that, let's say, the coefficient A1 is generally also 0. Why that?
I can't remember the details. You can have to read the books, and sometimes they don't bother to explain it, sometimes they spend several pages explaining it. That's standard. I don't want to try and explain it. That is quite general.
It's arbitrary. It can have any meaning if phi is 0, then of course, but why should it so? I would rather not try and provide an explanation of that. I would need to have another look at the textbooks to say that. But it is quite general. They all, any treatment of the Landau theory of phase transitions, very early on, knocks that term out. It says, just in one sentence, like I've said here, or might spend some pages trying to explain it.
Maybe it has to do with the trivial state or the ordered state, that should be at 0.
It's possibly something like that, yes. Well, yes, phi is 0 above the critical temperature.
It's like a Curie.
So it corresponds to a global minimum.
Yeah, and for us it goes.
When you say in your conclusion, could you the last one? Yes. When you say in your conclusion, the second part, that were not early prebiotic functional polymers, I don't think you can say that, because the synthesis of early prebiotic functional polymer are not well known. Such a synthesis are just beginning.
Yes.
So a lot of progress must be done in this field. And I'm not sure that...
Well, I'm trying to
something-
jump the gun here and saying in advance of all these experiments that you're not likely to find random heteropolypeptide sequences will be of any use, because they'll just finish up as
Yeah.
crud on the bottom of your
It's just my feeling.
Any statements at
Well,
all
it's-
here?
What is the difference, or what is actually complementarity between vibrational type of dichroism and ROV? Because I know that recently this method is becoming very popular, and the question is, where are the differences and what are the advantages of your method?
Right. Now, so Mayer is talking about this complementary technique called vibrational circular dichroism. This is the more obvious way to get a vibrational optical activity spectrum. You use infrared light and measure a difference in absorption of right and left circularly polarized infrared. So it's directly analogous to conventional circular dichroism, which is visible in ultraviolet. That had been known, the possibility had been known for 100 years, but the technology wasn't there to achieve it. Now it is there, and there's commercial instruments, and it's a very powerful technique for determining absolute configuration. In particular, ab initio simulations of BCD spectra can bring tears to the eyes. They're so perfect, the matching. You would stake your life, you would stake everybody's life on the absolute configuration that you can, by comparing the predicted pattern and the observed pattern. If all the, most of the signs are the same, then it's the absolute configuration is that for which you did the simulation. If they're all upside down, it's the opposite. And it's just as reliable as anomalous X-ray scattering. Just as ab initio, it's just as now VCDs. The lowest you can get, something like 800 to 1,000 wave numbers, so they just have that region there, first of all, because you need different optical elements for different ranges of the vibration spectrum. Whereas Raman, you see, this is the big advantage of Raman generally. You're analysing visible scattered light with a visible spectrometer. It's all visible. So you get the whole vibrational spectrum. We get down to below 100 here. And you can actually go up to over 4,000 wave numbers on the same instrument using a multi-channel detector. We don't bother to go to the higher wave number regions, the CH and CN stretches and whatnot, because the stereochemical, it's much weaker effects. So we get twice the spectral coverage. We can work very happily in water, which is the natural phonological medium. So that's a huge advantage over VCD. They have to work in D2O. And then in D2O, if you're studying proteins, you have hydrogen-deuterium exchange of the NH protons. And you don't know what you've got now in the solution. If you dissolve a protein in D2O, you get the sort of more exposed NH protons just exchange immediately, but some of the more buried ones can take months or years to exchange. So you don't know what you've got there, and it just messes up the spectrum, you see. No such problem with ROA. And as far as the ab initio simulations are now concerned, BCD was ahead of ROA on that for some years. ROA is more, you have to be more careful to get good quality simulations, and they're more expensive in computation time. But nowadays, you can get the quality of the ROA simulations are every bit as good as the BCD, every bit as good, and just as routine. But I mean, Philip Stevens, for instance, is the big. He developed all the ab initio stuff for BCD, and he's been pushing it, and beautiful results. But he's been a bit disparaging of ROA in that side of things. But it's not true now. It was a few years ago. But ROA was still good enough 10 years ago. The simulations were good enough to get the absolute configuration of this species correctly.
We have a problem actually with scales of trying to actually experiment. And the question is, what about solid state? Because I heard a lecture of, what is his name, in New York State,
Larry Lee?
Larry, yeah. And then he was presenting a lecture where he described that he can do the VCD of solid materials in KBR, like we use generally in infrared. And we tried, because this method may be useful for non-chiral molecules crystallizing in chiral space groups and integrating between the two, where X-ray doesn't allow it. And we have difficulties with that. Now, the question is, where is it? Do you think that it's possible to do solids? Because your viruses, actually, they are not homogeneous, if I understand, right?
Well, it's a solution of, we study a solution of the virus, and there's tremendous light scattering. It will blind you if you've looked at the laser beam going through the sample. But nonetheless, we pull out these beautiful ROA spectra. So, but they are isotropic, these samples. And in fact, with some viruses, those filamentous ones, if the concentration is too high, you get liquid crystal formation and you get big artifacts. So you have to dilute them down until we lose the liquid crystal formation. As far as solids are concerned, we cannot do amorphous. We can't do amorphous solids because you get multiple scattering depolarizes the light.
Then you lose the chirality.
Yeah.
Then you lose the chirality if you make it amorphous, then you lose the information.
Yeah. Now what we have done many years ago, beautiful spectra of single crystals of sodium chlorate and sodium bromate, fantastic strong ROA signals. So single crystals of cubical uniaxial single crystals, I think one could get good ROA data, and it would be very, very strong as well. You know, those virus spectra are remarkably intense, and that's because they're rigid, and rigidity gives a big boost to the ROA intensity.
How large this crystal must be in the sodium chloride?
Probably a couple of millimeters. It would need a lot of care. This is something we haven't gone back to, but it's something for the future, actually. It's something for the future.
As I told you yesterday, I'm impressed by the progress which was made in Raman spectroscopy. I used Raman spectroscopy 40 years ago.
Yes, with a mercury lamp.
Yes, exactly. Now, I think you have to have that in Raman spectroscopy you can obtain very nice spectra as you show, but in IR spectroscopy in water. But in IR spectroscopy in water, large,
very strong water
very strong
band,
band, so you can see anything. But in Raman spectroscopy, you can continue to observe very nice things. How many milligrams do you need of the sample to get such a spectrum?
For proteins and viruses, we need quite high concentrations, something like 20 milligrams per mil. But the actual amount of solid material we'd start with, we could get away with 1 or 2 milligrams. Something like 5 milligrams is a very comfortable quantity dissolved and put around little tiny cells. But if we're desperate, 1 milligram we can probably get.
Put it in a capillary?
No, we don't use a capillary because we use little quartz, little rectangular quartz microfluorescent cells. Little cells. We collect. Actually, we're doing backscattering. We collect the light in backscattering. Now, Werner Hug, who actually designs and builds this new generation of instrument, he has his sufficiently well tuned that he uses capillary tubes, in fact, and he did this one he did in a capillary tube, just a tiny quantity sealed up in a capillary tube. And he has sufficient control over artifacts and whatnot, and he got beautiful data.
I have a question. When you say something is completely disordered, obviously any one molecule has some particular structure. So you mean no two molecules in the sample have the same structure, or that it has some structure but no motif that's recognizable?
The latter. And when people talk about the random coil of a polymer backbone, I suppose if it's achiral, you could conceive of it being completely irregular, completely disordered, and it's dynamic.
What do you mean by completely disordered?
Well, the foci angles are being sampled equally over a certain time period. The torsion, the backbone torsion angles are changing, and you're sampling all possibilities.
But it's very, very unlikely that all structures are being sampled. Any particular sequence must have some bias in favor of some.
Well, I mean, this is something you should discuss with people like Howard Florio and whatnot, who developed a model of the random coil for the backbone of polymers. Obviously, if it's got chiral residues, chiral residues, then it's never completely disordered, is it?
But often people use disordered to mean I don't recognize it, therefore it must be disordered. And that's a very questionable definition of disorder.
Well, with polypeptide sequences, in a free polypeptide or a long chain hanging off the end of a structured domain in the protein, it's a sort of flexible disorder. But you have in loops in proteins, they can be rigid, and you can have the sequence of amino acids. Foci angles can correspond to the alpha region, and the next one the beta, the next one pp2, the type 2 turn, and that's what would be meant by disordered there. That's a static form of disorder. But obviously overall there's as you say, it's not completely.
This is related to the question about the technique. You say that you see much stronger signals from the backbone than from the residues.
Yes.
Is it because they are that the polarizability is especially sensitive to the vibration of those individual groups, or is it because there are many examples of the same group for the backbone, but residues, no two have exactly the same concentration?
Yes to both. It's because the backbone in a secondary structure, it's held fixed, it's rigid. It's rigid, and that does give a big boost to the ROA signal, whereas a side chain like
probably just a second, but I understand. So when you say it's rigid, you mean that all the molecules in the sample tend to have the same value.
Yeah, the foci
they're all
angles.
reinforcing.
That's right.
Okay.
Whereas the side chain, say a methyl group in alanine, you've got these rotational conformers present. And
Okay. But it must be that some groups have particularly strong what I might think of as oscillator strength. I don't suppose you call
they
it
do.
that.
Yeah. And it's not necessarily the same. The ROA oscillator strength isn't the same as the normal Raman. You can get very intense Raman bands, but little ROA. In fact, quite often you find the strongest ROA signals you get on very weak Raman bands.
So it isn't the sensitivity and the polarizability to the vibration.
Well, it's the chirality in the polarizability. In fact, you can develop a model of optical activity that's. You just look at the polarizabilities of, say, two groups held in a twisted arrangement and the way the light samples the twist as it bounces from one polarizable group to the other. You know,
So I assume that you have a very good intuition for this, so you can look at something and say, ah, that's going to be really strong. Is that true, or is this too much to expect?
probably.
Many questions, but I will concentrate on the instrumental question. Can you, with this instrumentation, follow kinetics long, non-stop?
No, because the measurements take too long. On a favourable sample, you can get a good spectrum of this stuff. In a couple of seconds, you'll see all the main features, but not.
With the PP2, or
The PP2, maybe on a good sample, maybe 10 minutes to be sure. Yes, but you'd leave a protein running for several hours or a virus all day to get the best signal. But we can do dynamic studies through temperature dependence. We can measure the spectrum at start at 0, 5 degrees, and we can watch proteins unfolding actually. We can go and say to the molecules what you
I
say.
know even of experiments. And the second question is, what about ugly anisotropy sample?
What about
Oriental, not anisotropy. Ugly
they're-
anisotropy.
They're,
How you call it?
they're deaf to this technique because you get huge artifacts. You must have an isotropic sample.
Yes,
Otherwise you're...
it's not possibility to get an
My question has been answered already.
Any more questions, comments? Your explanation is Lambda theory is mostly like phase separation from one phase. Am I right? If there's double minimum free energy, both L and T has a free energy minimum. So, and if it is bias, if the bias is small, not so many difference between L and T is generated, I suppose. Right, right. Maybe the next steps to amplify those small biases and equality.
Yes.
No comments and questions anymore? Thank you again.